All right, let's just jump right in. We all get the basic idea of vectors, right? They're basically just arrows. They've got a direction, they've got a length. But have you ever really stopped to think about how you multiply them? Because it is definitely not as simple as 2 times 2. Today, we're going to unpack the 2 super powerful tools that physics and math use to get this job done.
I mean, seriously, think about it. Adding them is a piece of cake. You just line them up, tip to tail. Subtraction, that's just adding the opposite arrow. But multiplication, I mean, what does it even mean to multiply 2 directions together? Well, the answer is actually pretty cool.
And this is where it gets really interesting. We don't just have one way to multiply vectors, we have 2 main ones. And no, this isn't just to make your math class tougher, it's because each one answers a completely different, fundamental question about how the world works.
So, let's pop open the Vector Multiplication Toolkit and see what we're working with. You'll see it's all about knowing which tool to grab for which job.
Okay, so the 2 big players on the field are the scalar product, which you might have heard of as the dot product, and the vector product, also known as the cross product. Let's break them down, one by one.
First up, we've got the scalar product. Now, I love calling this one the how much product because that's exactly the question it's built to answer.
So the official definition says you take 2 vectors, you do a little bit of math, and what it spits out is just a single number. That's it. Not another arrow, not a new direction, just a plain old number, or what we call a scalar.
So what that really boils down to is this. The scalar product is all about alignment. It's basically asking, hey, vector A, how much of U is really going in the same direction as vector B? If they're pointing the exact same way, you get the biggest number possible. If they're at a right angle to each other, totally out of alignment, you get 0. Simple as that.
And here is a fantastic way to picture this. Think of a shadow. Imagine the sun is shining straight down on top of one of your vectors. The dot product is literally the length of the shadow that the other vector casts onto the first one. It's a projection. It's just a pure measure of their overlap.
And the result is a number that actually means something. It's not just 50, it's 50 joules of work done, which is what you get when you multiply a force vector by a displacement vector. See, it tells you how much energy was used, not which way anything ended up going.
Okay, so let's grab our second tool. If the scalar product was all about how much, well, the vector product is all about which way.
And here is the absolute key difference. The vector, or cross product, takes 2 vectors, and it gives you back a brand new third vector. And the direction of this new guy is very specific. It's perfectly perpendicular at a 90-degree angle to both of the vectors you started with. It gives you a whole new direction to think about. You know, think of it like this. If your first 2 vectors are drawn flat on a piece of paper, their cross product is a new vector that points straight up out of the paper or straight down through it. It's basically a way to escape 2D and jump into the third dimension.
And the wrench is the perfect real-world example. When you're turning a bolt, right? The vector for your force is pulling sideways on the handle, and the vector for the wrench itself is pointing away from the bolt. But the actual action, the turning, happens in a third direction, totally perpendicular to both. That's torque, and that's a cross product in action.
So how do you know if that new vector points up or down? Easy. You use the right-hand rule. Seriously, try it right now. Point your index finger straight out. That's vector 1. Now point your middle finger out to the side at a right angle. See where your thumb is pointing? Straight up. That's the direction of your new vector.
So you see, the output here isn't just a number. It's a complete set of directions. It's a brand new vector with its own x, y, and z coordinates, perfect for describing things like rotation, torque, or even magnetic fields.
Okay, so we've met our 2 tools. Let's put them side by side for a final showdown just to make sure the difference really sticks.
This table really just says it all, doesn't it? The scalar, or dot product, asks how much alignment is there. The result is just a number. Your keyword is shadow. The vector, or cross product, asks which new way do we go? The result is a whole new vector. Your keyword is wrench. 2 totally different questions, leading to 2 totally different kinds of answers.
So why does any of this actually matter? I mean, who cares? Well, you should, because these aren't just some abstract problems in a textbook. These tools are used literally everywhere to describe and build the world around us. I mean, look at this. In physics, you've got the scalar product for work and the vector product for torque. And get this, in computer graphics, these calculations are what determine how light bounces off a 3D model to make video games look so realistic.
Engineers use them for analyzing forces on a bridge, and GPS and navigation systems use them constantly to figure out orientation in 3D space.
So if there's one thing to take away from all this, it's that these two ways of multiplying vectors are so much more than just math. They are a fundamental part of the language we use to describe everything, from something as simple as pushing a box across the floor to something as complex as guiding a spacecraft through our solar system.
Which kind of leaves us with one final thought. Now that you speak a little bit of the language, now that you know the difference between asking how much and asking which way, where else do you see it? What other parts of our world do you think are secretly being run by this hidden, powerful logic of vectors?